let's work the 1993 E&M FRQ number 2. And if you're going to work on other stuff, that's fine, but you got to be quiet. And if you really want to talk and stuff, and I don't know what Evan's doing. Look at him over there. Come on, Evan. Are you working on stuff? This is recorded for posterity, so 20 years from now, students will wonder, who is Evan? All right. Now, yeah, because I'm never going to make these again. All right, so here's FRQ number 2. So we've got this, we got a rectangular loop of copper. So here's our rectangular loop of copper of resistance R. So that's the total resistance of this. Has a width of A and a length of B, as shown. The loop is stationary in a constant uniform electric field, B naught, directed into the page as shown. So it's stationary. We have a trick question. All right. So, well, actually not really. So for part A, what is the net magnetic flux through the loop? So that's AI. So let's do that first. And so what you have to know is what is the equation for magnetic flux? Well, it doesn't have to be a closed integral. In fact, if it was, okay, yeah, this is B dot dA. Now, by the way, I'm glad you brought this up. What if you put a closed integral sign here? It's going to be equal to 0. But so this only gives you a value if it's if it's not a closed surface. Okay. Okay. So this is the magnetic flux, and so let's figure it out. So B is uniform, so it's just B naught, and then the area is just A times B. So there's your answer. Pretty easy. And it spells Boab. I don't know, but yeah, they give you easy ones. Sometimes they give you ones that are so easy you go, that can't be right. It's so easy. But they they're just trying to throw you a fish, All right, so what is the induced EMF in the loop of the wire? Now, don't just say it's 0. Okay? I would do this. I would say the induced EMF is equal to negative, I would show off a little bit, dB dt, right? But I would say this. The magnetic flux is constant here. Therefore, E equals 0. The induced EMF is 0. Right? Because if your magnetic flux contained by a loop of wire is not changing, you'll get no induced current, there's no induced voltage. But don't just say 0, you guys. On the AP test, show what you know, justify it. They want to give you points, but they can't just give you points for, 0. Well, they might, I don't know, but they won't give you all of them. Okay. And it says, what is the net magnetic force on the loop of the wire? Well, the magnetic force, you have F equals, I, L, cross B. I don't know if I would even do this. You didn't really have to do this. But there's no induced current. No induced current. Therefore, F equals F sub B, I guess we'll call it, equals 0. So in other words, there's nothing going on here in part A. Nothing interesting anyway. Okay, now we get to the interesting stuff that involves induction. Guaranteed you're going to have an induction problem like this on the test, on the AP test. It says, suppose instead that the uniform magnetic field varies with time, t, according to the relationship B equals B naught cosine omega t, where omega and B naught are positive constants and B is positive when the field is directed into the page. So we got this function here. Indicate the on the diagram below the direction of the induced current in the loop when omega t equals pi over 2 after the magnetic field begins to oscillate. Okay, this one's a little tricky. Every year this one kind of makes me scratch my head for a few minutes. So here's my loop of wire. Yes. And so E is equal to, now the negative is Lenz's law here, so that negative is going to help us figure out what is going on here. But, I think what I'm going to do, well, let's go ahead and finish my thought here. And, so let's write an equation. So B is originally directed into the paper like this, and B is equal to B naught times cosine omega t. Okay, now I actually have to visualize stuff. So I know that this is equal to negative. Well, the area doesn't change, so I'm just going to put the area comes out, and this is going to be dB dt, where B is this function right here. And so I'm just going to graph B for a second. So at omega t equals pi over 2, that's 1/4 of our way. So I'm going to graph the magnetic field here just to help me visualize it. Probably, if you can visualize this in your head, you probably don't need to do this. But when here's pi over 2 right here, right? Because this is pi. It's 3 pi over 2, 2 pi. So here's pi right here. Now what's the magnetic field? So it's going to be 0, but in other words, the magnetic field was into the page, wasn't it? But it's less and less and less and less into the page, and here we have the maximum rate of change of magnetic flux, and pretty soon now it's going to be out of the page, and it says, no, I don't like change. Don't change. Keep the flux going into the page, please. And so it will induce a current that will induce a magnet or create a magnetic field that goes into the page. So you take it with your right hand rule. Let me zoom out so you can see the right hand rule. And so it's going to try to create a current that's in this direction. Okay? So is that right? Clockwise? Is that the right answer? Please tell me that's the right answer, because I have done this one wrong before. But now, so anyway, this is the way I have to do it. I have to do it by talking about and thinking about the magnetic field's function there. Any questions on that? All right. So then part C, it says, derive the expression for the magnitude of the induced current in the loop as a function of time. And we already kind of started part C. I did. So that's okay. Let me just redo it up here. I'll just do it right next to it. I could squeeze it down here. So part C, I kind of started it up here. So E is equal to, let's finish this, negative AB. Now they want for the magnitude of the induced, of the current. We already know just the magnitude of the current. So I don't really need to worry about that negative sign. I'll drop it here in a second. This is dB dt, and B is equal to B naught cosine omega t. And so this is going to be, let's just A, B, B naught, and then we need to take the derivative of this. I pulled the B naught out. What's the derivative of cosine omega t with respect to t?
Negative sine. Wait, omega negative sine t. Omega
Yeah. So let's just let that negative cancel that a negative, and then this will be omega sine omega t, right? You got to use that chain rule. You got to take the derivative of the inside part. Now that's the expression for the induced voltage, but now we can use Ohm's law, where, you know, you're getting towards the edge of the paper here. E equals IR. So all you have to do to solve for I is divide all this mess by R. So A, B, B naught omega sine omega t, sorry, over R. And there's my answer for part C. Is that right?
Yes.
Okay. I hope this, you know, Faraday's law is starting to come to you guys, right? I mean, we got, well, 2 weeks from today is the test, right?
What?
Yeah.
It's 2 weeks from today.
So,
I'm not getting a 5.
well, you can. Don't worry. Everybody's in the same boat with this stuff, you guys. I don't know how many, like 50 or 60,000 students take the test. And
Were you about to say the stupid test late?
no, take this test.
You told me.
No, you're making stuff up again, Dilpreet.
No, I'm not.
And so you're hearing.
You're on camera. Don't deny it.
Hey, it's on video, and I did not say stupid test.
You were about to.
This wonderful test. All right.
This slender.
Okay, now. Okay, please shut up now. Thank you. Here's 2. It says, on the axis below, sketch a graph of the induced current I versus omega 2, taking clockwise to be positive current. Oh, great. All right, so clockwise, well, we know it's going at its maximum there. And so we took the derivative of this. And but at omega t, we knew that at omega t, we said that the current was at its maximum clockwise. So what we're going to do is this. We're going to say that it was started at 0. I mean, when you look at the graph of the magnetic field, and then remember, this is just a graph right here of B as a function of t, not of the, you know, and so we had no slope right there. That means no change, which means no induced voltage, which means no induced current. So it's going to start at 0, and then it's going to reach its maximum, which is A, B, B naught omega over R. That's the maximum here. And so it'll look like that. Something like, oh, I wasn't going to draw on this. Doggone it. All right. So does that make sense? Okay, because we said at pi over 2 that it was, you know, going clockwise, and we're taking clockwise to be positive, so it's going to go from 0 to positive. It's positive, and I don't know. Did they want this maximum current on the graph? Those of you who have the solution manual.
It's not in there.
Oh, okay.
All it is the sine wave that shows it period 2 times.
Okay.
So it's that's a super easy.
So there you go. State explicitly the maximum value of the current I. All right. Well, then you just put it on the graph.
Yeah.
Like that.
Just draw an arrow.
Yeah. Okay. And I think that finishes E&M problem number 2. And then tomorrow we'll do E&M problem number 3. Woo-hoo.